Hi, we're going to solve this heat transfer problem using some methods that we haven't quite covered yet in class. So I'm going to do a quick crash course so that we're able to solve this problem. So the problem states, compute the temperature profile for a 4-inch long by 1/8 inch thick black aluminum fin that is 1 inch wide. The base of the fin has been measured to be near 120 degrees C. You may assume the free convective heat transfer coefficient to be 7 due to 25 degrees C air, which is surrounding the fin. Assume the emissivity of the fin is 0.9 and the surroundings are also at 25 degrees C. Okay, so this is a special type of problem where we're going to make what's called a thin fin approximation. And we're going to do that because, so here we have some base, and this is where it is at 120 degrees C. So this will ultimately become a boundary condition. But then this fin is 4 inches long, but it's actually quite thin. It's only 1/4 of an inch thick, and then it is kind of wide. So what we're going to do is we're going to make this what's called a thin fin approximation. We're going to assume that because it's so thin, that temperature does not vary in the y or the z directions. We're going to assume that temperature only varies in the x direction. And what we want to do is calculate the temperature profile as a function of x, however that is going to look. So we've done this before with the heat equation, and this problem is actually a little bit different than the heat equation, and that is because we are dealing with a material that is thin, and so it's exposed to, this particular problem is exposed to convection and radiation all along the way. So using this one-dimensional approximation, we're going to take this fin and we're going to break it up into smaller control volumes or nodes going in just the one direction. But because it's not purely conduction in every node, so here we're going to have conduction going this way. But then for every node, we're also going to have both convective and radiative heat transfer here. So so this problem ends up has similarities to the heat equation, but differences also because it's not just conducting in all three dimensions. It is convecting and radiating in these directions out of the surface area. All right, so using this thin fin approximation and assuming that temperature only varies in one direction, what we're going to do is we're going to take each of these control volumes that I just mentioned. We'll call them nodes, so throughout this video you might hear me refer to them as nodes as well. So what we're going to do is we're going to break each of these up. We're going to do an energy balance on each one of these. So I'm going to just make my control volume a little bit better here. So what I'm going to do is I'm going to assume that this node is the ith node. This one is the I-1 node, and this is the I+1 node. Again, our base here is hotter, so we're going to assume conduction happening from left to right. So I'm going to create a control volume and do that control volume around this one node. This will be my system basically, and I'll do this energy balance here. In this problem, we're going to assume steady state, and unfortunately that is not expressed in the problem, but this is a steady state problem. So when we write out our energy balance, we have our accumulation term is equal to 0. We can have an in term and an out term, and we're also assuming that generation is not occurring within our solid fin. So our generation is also going to be 0. So we want to think about how is energy getting in and out of our node. So if we think about conduction happening, so we have conduction happening, again assuming that it's hotter on the left, energy is going to be flowing from left to right, so it's going to be conducting in. So here we would apply Fourier's law for conduction, which would be minus k dt dx multiplied by our cross-sectional area. What we're going to do is we're going to end up solving this problem numerically. Because this problem has radiation in it, it makes it really difficult to get an analytical solution. But we'll find that we can solve it by numerically using tools. We're going to use Excel for this problem, but you could use MATLAB or Python solvers just as well. So because we're going to solve it numerically, we're actually not going to get to the point where we shrink our control volume down to be infinitesimally small. What we're going to do is use a lot of these nodes so that the more we use, the better resolution we get. And this approximation that dt dx is approximately equal to delta t over delta x is one that we're going to make here. So rather than using this gradient form of Fourier's law, we're going to assume that we shrink our control volume down to be thin enough in terms of delta x that we can do a temperature difference here. So in this case, our delta t over delta x approximation is going to look like the temperature of the ith node minus the temperature of the I minus 1 node, because again, energy is crossing this boundary, divided by delta x, and here we will still use our cross-sectional area. So going out of this node, we also still have conduction. So leaving this node is going to be something similar. So we're going to use that same finite difference approximation, and we're going to go minus k times the temperature of the I plus 1 node minus the temperature of the ith node, also over delta x, and that also needs to be multiplied by our cross-sectional area. So we use this, again, the approximation of the derivative in finite difference terms. We use the forward temperature minus the backward temperature divided by our delta x. So an interesting thing in this problem is we also have convection and radiation leaving. So we're going to have these other terms. Our convective out term is going to be so because we're assuming, so in this individual node, we're going to assume that it is uniform in temperature all around. So we're going to treat the Ti as being uniform. So that means it would convect uniformly out. So in this case, we would have our Newton's law of cooling term is going to be H. And now what we want to do is use the surface area. So if this is our node here, the surface area is going to be the summation of the area here and the area here. So we'd have basically 2 multiplied by the thickness times our delta x plus 2 multiplied by our width times delta x. And we multiply by the 2 because we have a top and a bottom and a front and a back. So that's what will be contained in our surface area term. So to complete Newton's law of cooling, we're going to use the temperature of the ith node minus our ambient temperature, which is given in the problem. So our ambient temperature is 25 degrees C. Similarly, for radiation, we're going to have the Stefan-Boltzmann law here for heat loss due to radiation. So we're going to have the emissivity times the Stefan-Boltzmann constant. We would use that same surface area, and now we're going to use Ti to the 4th, and we're also given in this problem our T surroundings, that's going to be to the 4th as well. So our energy balance becomes accumulation equals in minus out plus generation. So we're just going to have this 0 over here. Our in is going to be minus k times Ti minus Ti minus 1 over delta x multiplied by the cross-sectional area. So now it's in minus out. So everything that's in this out term is going to get multiplied by a minus 1. So this becomes a plus for the out term on conduction. So here we have minus k Ti plus 1 minus Ti divided by delta x times our cross-sectional area. And then the minus now makes the Newton's law of cooling term be a negative. So here we're going to have minus h times the surface area now, times Ti minus T infinity. And then we also subtract off this radiation loss term, which is sigma, epsilon times sigma times our surface area, Ti to the fourth minus T surroundings to the fourth. All right, so what we've done basically, some people call this a shell balance, where you, if it's a one-dimensional system, you divide that one dimension up into these smaller control volumes or shells. And what we could do here is we could translate this into a partial differential equation by taking the limit as delta x approaches 0. So that would give us a PDE, which we would then try to solve analytically. We're not going to do that. We're going to do instead a numerical approximation of this partial differential equation. And what we'll do is we will, oh, and I misspoke. This would actually be an ordinary differential equation. But we're not actually going to turn it into an ODE and solve it, largely because this radiation term makes that pretty difficult to do. So rather, we're going to do a numerical approximation by just taking this energy balance and computing it for all of these different nodes simultaneously. So I'm going to jump over to Excel now and teach you kind of a simplistic way of solving a problem like this. So what I've done in this Excel template is I have taken all of our units here. So the length of this is 4 inches. I've converted that from imperial to SI units, so from inches to meters here. I've done the same with our thickness and with our width. So these are all in meters. With our base temperature is 120 degrees C, so I've converted that to Kelvin. Our H and our K are already in SI units, so no conversion needed there. We've converted the ambient temperature and the temperature of the surroundings here. Our emissivity is unitless. Sigma is already in SI units, so we're all good there. And then what I've done is I will get back to this actually. So what I'm going to do here is I'm going to give us let's do a distance. So we're talking about distance down the length of this thing. So our distance is our x variable. So I'm going to break this up into these different nodes and talk about different distances. So here our distance, or x. What I'm going to do is give each of these nodes a number. So I'm going to break our control volume up into 20 nodes, just to give us good resolution. So this is remember the system is 4 inches long, so breaking it up into 20 nodes give us a dx of 0.2. And so that's what I've done here, is I've taken our length, divided that by the number of nodes. So our delta x that we're going to keep as a finite number is 0.2 inches. We convert that to meters and it becomes this other smaller number. All right, so now what we want to do, just for clarity, when I think of plotting this with respect to temperature, I'm just thinking of we're making this approximation that each node is uniform in temperature. So really, it's the same temperature everywhere throughout that node is the approximation that we're making. But just for plotting purposes, I like to think of our node being represented spatially by the center point there. So the way that changes, so I like to start here with this distance is our dx over 2 for the first node. So that's just the midpoint of the first node. And then from that point on, I just say the rest of the nodes are dx away from that one. So I'm going to do a little trick here. If you have not used Excel for calculations here, I'm going to give this other distance an absolute reference. So when my cursor is on this cell reference C12, I'm going to click the F4 button on my PC. And I forget, this may be different on a Mac, so you'll just have to figure out how to do that. So what that does is it makes it so that this creates an absolute cell reference. It means it's going to reference the absolute column and the absolute row. So notice how that translates. When I take this cell and now copy it all the way down to the bottom, this will give me, so here this cell, it's equal to the distance of the previous cell plus this absolute delta x. So we're going to be using this trick as we go to make our life a lot easier. All right, so in this other column, I am going to create a temperature column. So I'm going to put my temperatures here. We don't actually know what these temperatures are yet, so I'm going to guess here. So our base temperature is at 393 Kelvin, so I'm just going to put in a guess of 393. So I will take that guess, copy it all the way down to the other nodes. All right, so then we've got our temperature, which is in Kelvin. All right, so now what I'm going to do, so throughout class, we've used an energy balance to give us an equation, and then we use that equation to solve for an unknown. So currently, because we have 20 nodes, we have 20 unknown temperatures. So we're going to need 20 equations here. So what I'm going to do is I'm going to create this other column called the energy balance column. And in this column, I am going to essentially go and plug in this energy balance that we just wrote. So I'm going to start here. I'm not going to start at this first node because that's going to be a special case where we need to input our boundary condition. So rather I'm going to start here. And I'm going to be using that absolute cell reference trick that I just showed you. So now our job is to go through and type in this energy balance. So we've got it written down already. So what I want to do is I want to put, we know the left-hand side of our equation is 0. So we want to put everything that should show up in the right-hand side, and then ultimately we're going to solve for our unknown temperatures until all of them simultaneously equal 0. All right, so I'm going to take this second node, let's call this the ith node, and I'm going to start typing this guy in. So here we have, I've used the equal sign, we have our conduction in term, so we have minus K, and I'm going to be referencing this cell repeatedly and copy this down, so I want to use an absolute reference there. So minus K multiplied by our temperature difference. So here it's the temperature of the ith node minus the temperature of the I minus 1th node. I have minus K, Ti minus 1 divided by, and now I have this delta X term here. I also want that to be an absolute reference. So that's our conduction in term. Our conduction out term, oh, and I forgot to multiply that by our cross-sectional area, which I have also computed, but I skipped the explanation there. But that's easy enough to figure out. Okay, so that is our conduction in term. Now we need our conduction out term, which if you recall, because the minus sign in Fourier's law, this ends up having a plus sign. So here I've got plus K, again, absolute reference with the F4 key. So now I'm going to use this forward temperature difference, Ti plus 1, oh, and I need a parenthesis there, Ti plus 1 minus Ti, divide by dx, absolute reference, multiplied by the cross-sectional area, and absolute reference there. Okay, this is a little tedious and can be a little long and complicated, but this will make our lives a lot easier as we go. All right, so I have my conduction in term, my conduction out term. I now need my convection term, which was minus H times our surface area now, and the H and surface area are both going to be an absolute reference. So now this is the temperature of our particular node. I want to keep this as a relative reference minus the temperature of our fluid. This one's going to be an absolute reference because I want to use the same temperature in all the nodes. And finally we have our radiation term, which is going to be epsilon absolute reference times sigma absolute reference times that same surface area that we used for convection, multiplied by, now we use our our node temperature to the fourth minus the surrounding temperature. And that one needs to be an absolute reference to the fourth. Okay, and I hope we got everything in there. We will see how this works. So now I hit enter. Another thing that's worth mentioning, I converted all of our temperatures to Kelvin, and actually, yeah, this one was actually, this isn't imperial units, this is going from degrees C to Kelvin, so that's my mistake there. But we converted everything here to Kelvin because we know that there's radiation in this problem, and we're going to be taking temperatures to the fourth power. So here we need to use absolute temperatures. All right, we've got this energy balance done, and what I'm going to do is I'm going to copy this down all the way down to the bottom. And I'm actually going to copy it up here as well. So for all of these nodes, we've done, for all the nodes that are here, 2 through n minus 1, those all basically have the same form of the equation. But because we're approximating this ordinary differential equation, that's a second order ordinary differential equation, we need to have 2 boundary conditions. So we'll need a boundary condition for each end of this. Our boundary condition for the base will be just that this node has energy conducting in from the base temperature, from the base. On this end, we could apply a number of different boundary conditions. I'm going to use the simplest one here, which is just that we're just assuming that this end is so small in terms of area that convection and radiation out of it are negligible. So we're going to use a zero flux boundary condition. We could use a convection and radiation boundary condition, but we're going to make our lives a little bit simpler, and we'll find that if we try those different boundary conditions, it doesn't change the solution dramatically. All right, so the way that we enforce our boundary condition, notice that this cell is giving us an error here. And notice that when we look at the cells that this one is referencing, it's trying to reference this number here that isn't actually a number, it's the letter T. So that's because this is the conduction in term. And really what's happening here is it can't conduct from any other nodes because this is the first node. So a simple way to do that is we're going to say this is actually, it's conducting from this base temperature. And that is basically the way that we enforce our base temperature boundary condition. On the other end, we'll notice that this cell is giving us, I think it's giving us a number, but it's not correct. And when we look at what this cell is referencing, so notice it has this conduction out term that is referencing a cell where there's no number in there. So what we can do is we can go back, and here's our conduction out term. And actually what we can do is just replace this whole thing with 0, or we could just delete the whole thing entirely. And that is essentially the same thing as a zero flux boundary condition, because we just deleted the only way that energy would be getting out, and we have not included a convection or a radiation term going from this end here. All right, so I mentioned this lesson is a little bit out of sequence for the rest of the class, so we'll do more problems like this, and hopefully you'll get into a groove there. So what we've done here is we have now our 20 unknowns, all these different temperatures, and now we've created this energy balance equation for all of these. So remember that the right-hand side, in every case, we want that to be equal to 0, but it's not equal to 0, it's equal to minus 0.43. So what we want to do is we want to iterate on these temperatures until we get a temperature profile that satisfies every single energy balance simultaneously. So what I'm going to do is I'm going to use this tool in Excel called Solver. So I go to my Data tab and go to Solver. Okay, give me a second here. If you do not, you'll find that by default, if you've never used Solver before, okay, I want this to go away right now. If you've never used Solver before, I'll show you how to add that in, and I'm just going to try and fix this error really quick. So this will leave me alone. If you've never used Solver before, I believe you can go here to File, and then there should be this Options. So go to File, Options, Add-ins. And then there should be, if you go to Manage Excel Add-ins, you just go click this box for Solver Add-in, and then on the Data tab, you should see this Solver appear. So Solver is a pretty remarkable and very powerful tool, and so that's why I wanted to cover this in class. So what I want to do, I go to Solver. Solver is set up to do optimization problems, which we're not doing. So we just want to pick one of these energy balances, pick the cell there. I'll just pick our first energy balance, whoops. And I'm going to set that to a value of 0. I'm going to give this, I'm going to tell this, okay, what are my unknowns? Which are the things that I'm iterating on? So I'm going to be iterating on all of these temperatures. And now I need to give this some constraints. So I'm going to go here to add constraints, and the constraint is solve all of my energy balances until they're all satisfied, meaning that the right-hand side equals 0, because we know the left-hand side equals 0 because it's this steady-state problem. So I've selected all of those cells, and collectively I want all of them to be equal to 0. So I click OK to add my constraint. I don't think we need to worry. We're already using this GRG nonlinear method, which is good enough to solve this problem. And I'm going to go here and click Solve. So what Solver did very quickly was it went through and iterated on all of those temperatures until it found all 20 temperatures that simultaneously made all of my energy balances converge. So you can notice these are much smaller numbers now. So it's not perfect exactly 0, but it is very close. So that gives me this temperature profile. Note that this is in Kelvin, but I can go here now and I can plot what this temperature profile looks like. Again, this is in Kelvin. So we see that we start up here near our base temperature of 393, and then it's gradually cooling, and it ends up with a tip temperature of about 374 Kelvin in this case. So the problem, just so we're complete here, oh, and I am actually not, well, the actual problem that was assigned to the class was to calculate the temperature profile, but also calculate the amount of energy in total leaving our system. So what I'm going to do, just to provide a little bit of insight, is I'm going to calculate the convective heat loss and also the radiative heat loss. So because we already know the temperatures now, I can go plug in Newton's law of cooling here. So here I'm going to use H times our surface area of each node times now the temperature of that cell minus the ambient temperature, which is here. And I want that to be an absolute reference, but I want my cell temperature to be relative reference. And I've done a unit check before all of this, and I know that these units are watts. So this particular node loses 0.2 watts by convection. So now we should be able to safely copy all of that down, and we are able to see, well, because the temperature is decreasing for every node, that our Q is a little bit less each time as well. For radiation, we would do something similar. So we're going to look at epsilon multiplied by sigma multiplied by that same surface area multiplied by our node temperature to the 4th power minus the temperature of the surroundings. And I want this one to be absolute to the 4th power. And I think we should be good to go there. So here the radiation heat loss is actually a little bit higher, but on the same order of magnitude, so 0.23 watts for the first node. I'm going to copy that all down. And so in the problem statement that was given, you actually need to calculate the total rate of heat loss for the fin. So I'm just going to sum these up for convection first. And then for conduction, for radiation. And then if we get the sum of the total of those, we get about 7.2 watts. So that is how you would solve a problem like this using a numerical solution.